now going to discuss about the Riemann integral, and that is part 1, and part 2 essentially talks about improper integrals, but I just called it Riemann integral 2 because when you talk about Riemann integral, you are not really in the truly in the domain of just what you call calculus. It is slightly advanced calculus, otherwise I would say it is called mathematical analysis. You are taking a very deeper look into the issues of calculus. So, my idea is not to give a very deep mathematical idea or very rigorous idea of what is Riemann integral, but I would just like to tell you that this was an idea which was quite important in those times in the 19th century, where you move forward from the idea of just integrating continuous functions to the idea of integrating bounded functions, and it was introduced by Bernhard Riemann, one of the greatest mathematicians of all times. Now, sorry, Bernhard HRD. I do not know whether I am writing it. I think it is the correct spelling. So, what was his idea? His idea was pretty simple, that suppose I just have a look, if you observe a curve like the continuous function, you know how to find the area, you already have studied in school, but now suppose I have a function like this, which is here, and then it is discontinuous, it is from here, it is here, and then I am trying to find the area between this point A and this point B. Do they have an area? Can we define an area under this curve? You might feel okay, slightly problematic at this end point, but I would say why bother, just compute the area of this rectangular zone and just compute the area of this, which can also be easily computed, or you can also take a rectangular. So, you for example, in electrical engineering what you have is step functions, is which is something to do with switching circuits. It is called Heaviside step function. So, do they have an area? Observe that if I want to find the area from A to B, I would really can easily define an area under this curve by just computing out the area of these rectangles. See, the idea is interesting in the sense, now if a function is bounded, Riemann said that you can extend the concept of Newton's integration from continuous functions to bounded functions, because every bounded function need not be continuous, because here we see that these two functions are bounded functions, but discontinuous at several points. So, how do I look at such a function? Okay, let me make a drawing. So, Riemann's vision was the following, that let us just take this curve, the graph of a bounded function, let us just for just heck we take one discontinuity. So, the discontinuity of the function does not have any, sorry, I will just make it much more easy. So, the function comes up to here, but does not have any value on at this point, which is C. So, how do I start integrating? What we do is, let us forget this C point for the time being. At the C the value is this, so there is a discontinuity, but the function is bounded. What we do is, let us divide this whole line AB into some partitions of equal length, or may not be equal length, but okay, does not matter. So, this is say x1, so A I put as x0, this is x1, x2, x3 and dot 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 x I and so this is x n. So, what we are doing, we are drawing rectangles, we are just joining up and drawing one set of rectangles, just joining up with the upper part of the graph. Okay, let me draw the partition just slightly clearly. These are my partition points. So, what Riemann did was, okay, said okay, the function is bounded. So, whichever partition I take, say I take this partition, the function has a maximum value and a minimum value. Here the minimum value is obtained at A. So, taking this height as f a, draw a rectangle. The same case you do with the point x 1. So, here the minimum value is x 1, the function here is increasing, but here the minimum value is also the function is increasing. So, you take it here. Here also it is increasing, you take it up. So, you take the minimum values here, 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 here and here. So, now you take the minimum value over that interval, take it as the height of the rectangle, and with the base as the length of the interval, compute the area of the rectangle. So, if you sum of that area, so what I am doing, I am taking for each interval m k as the infimum. It is obviously it is achieved because of here the function is bounded. So, it is the infimum of f x when x is lying between, you can okay, just for the heck of computation, just for the simplicity, put m k to be between x k minus 1 and x k. You can take the otherwise also, shift it, you can take between x k plus 1 and x k, that also you can take as x m k, and then you, the writing would be slightly simpler if you do this, that is not a very big issue. Similarly, if you look at the supremum, you can actually construct rectangles with the supremums. So, now what you can do, you can with the small ones, this is the area of the kth partition actually. Oh, we have taken x 0, right. So, x 0 means I have to take m k in this form, x 0 is a. So, taking the whole thing for the kth partition, now you sum this up for k is equal to 0 to n. Now, this one is called the lower Riemann sum, actually it is called the lower Darboux sum of f under a partition pi, where pi is the partition A is equal to x 0, x 1, x 2. So, the n point so 1 points. So, there are n intervals actually. So, I should start from k equal to 1, then it will give you x 0, x 1 minus x 0 and m 1. So, if you take 1 here, so k can be starting from 1 to n. If you take k 1, so it is the infimum between when x is in between x 0 and x 1. So, that is the thing. So, this is called the lower Riemann sum. Similarly, you can construct the upper Riemann sum. So, if you write m k as the supremum of f x between when x is lying between x k minus 1 and x k, then you can similarly compute what is called the upper Riemann sum or u f phi. Pi is this partition, pi is called the partition. and then if once you construct this sum, this will become say k equal to 1 to m k x k minus x k minus 1. I do not want to leave this page because you finally have to understand things here. So, I just rub this off and talk to you. So, what I have now done, if you look at the picture, the actual area of the actual area under the curve is sandwiched between this area, the upper Riemann sum of the and the lower Riemann sum. So, the actual area, if we call it the integral, if I call it the integral, which we will call the Riemann integral very soon, is for any given partition pi okay, this inequality might be strict. Now, suppose we take the supremum of L f pi for all possible partitions pi, and we take the infimum of the upper Riemann sum for all possible partitions pi. When I say pi, it means over this supremum over pi means all possible partitions. So, there are countably just the infinite possible partitions, partition in this way, partition this one partition, that you can have any other partition. There can be any many ways of infinite ways of partition, countable infinite ways. This is one way of partition, there is then the second way of partition, the third way of partition, and just can go on, countably infinite ways of partitioning. And then I just take, I will make I will partition in such a way that I will make the interval lengths, that is x I and xi minus 1 and xi or xk minus 1 and xk, this interval length is made smaller and smaller and smaller. So, if I call this interval length as delta xk, then I will make delta xk go towards 0. I will make it smaller and smaller and smaller, and then I will see what is the supremum of LPF, and so what happens to this. Of course, if you look at this inequality, then it will always be like this. But if supremum of pi L f pi is equal to infimum of pi u f pi, then we say the Riemann integral exists, and infimum of u f pi for all partition pi and supremum of L f pi for all partitions pi is actually called the integral of a to b from f x dx, and this integral is called the Riemann integral. So, we will not go to too much of a discussion on Riemann integrability. So, let us tell you what sort of functions are Riemann integrable. Every continuous function on AB is Riemann integrable. So, any function for which the Riemann integral exists, we call it Riemann integrable. Now, take every, and now the interesting fact, what we have just seen, that we have done this game with a discontinuous function at just as one point of discontinuity. So, if f is bounded on AB and has only finite number of discontinuities, then f is Riemann integrable. Is there any function bounded but not Riemann integrable? This function was handed over to Riemann by his thesis supervisor Dirichlet, and this is the famous Dirichlet function we have already spoken about earlier. The fx is equal to 1 when x is rational, that is x is in the set Q, and is equal to 0 when x is not a rational number, when it is a irrational number. Now, I want to integrate it. Now, let me see, I will partition it. So, I will partition, so let me partition it, just do it between 0 and 1. So, I want to ask what happens to this for this particular function. Of course, this is a bounded function, the values are only 0 and 1. Now, if I partition it, whatever be my partition, because there are always infinite number of rational and infinite number of irrational numbers inside those partitions, my upper Riemann sum, it does not matter for any whatever be the partition pi, my upper Riemann sum UF pi is nothing but 1 into summation delta xi over I equal to, or delta xk over k equal to 1 to n. So, when if you sum of the partition, it will give you b minus a, but when you take the lower partition, it will be always 0 into delta xk. Which is 0. So, if you take the infimum of the lower Riemann sum, upper Riemann sum for all possible partitions for all pi. Pi is not the real pi, okay. If you are uncomfortable, I will just put this partition as pi hat like this. Maybe people don't want to confuse it with actual partitions, an actual pi the number, but it is 0. So, this is always b minus a, and this is the supremum of LF pi is always 0 for taken over any pi, all possible pi's. So, what happens that because b minus a is strictly bigger than 0, here it is b minus a basically, here b is 1 and a is 0. So, this is 1. So, they are not equal. So, this implies that 0 to 1 fx dx is not Riemann integrable. I will just mention one or two more properties of Riemann integrability. So, if something like that, if f t is less than equal to g t for all t element of a b, where each f and g are Riemann integrable. So, we just write for short R integrable, both of them, then you will have that integral a to b f t dt is less than equal to integral a to b g t dt, where both a and b, f and g are two functions which are bounded and has this property. And also you will have the property which is a consequence of this is the following property. This happens because f of x, it does not matter whether it is plus or minus, is always less than modulus of f(x). So, if f is a bounded function, then mod f is a bounded function, and if f is integrable, then mod f is also integrable. So, and that is why this happens. So, with this very little ideas, or all other things like happens for continuous function, the summing up of two functions and integrating the sum is same as integrating the function separately and summing them up. Those sort of things remain same for all, those properties remain same in toto like the ones you have learnt for continuous function even in high school. So, with these very simple ideas here and with this very simple way of looking at how to integrate functions which are not even continuous and just bounded, we stop our discussion of the Riemann integral part 1. And in part 2 we are going to talk about something called improper integral, where one of these b or a are points where b could be just infinity, or one of these points are such that the function is not defined at that point. We will just go into that in 5 minutes in the next lecture.